Welcome to Innovation Insights for June 2021. We've got another exciting program for you today. Just a little bit about it. What Innovation Insights is, it's a monthly webinar series. This is our second one that features products and technologies from our industry members and core R&D partners. So typically what we'll do is have one small company, one large company, and one research partner be presenting on some new products or new technologies. Anybody that's an IACMI member in good standing is eligible to present at one of these monthly webinars. So please get a hold of me if you want to get on the schedule, and we'll talk about the schedule in a little bit. Just a reminder about IACMI. We're the National Composites Institute. Our core themes are to convene, connect, and catalyze, bring people together, connect people together, and then foster innovation and development and commercialization in the composites industries. And with a lot of supporting things that go around it, from the networking to education, from facilities to intern training, consulting, and our corporate meetings and things like that. We do have resources and facilities available for use, open access facilities to do demonstrations at scale, digital tools for design and analysis and modeling simulation, and then the workforce development capability that is very important. We believe we're a connected community. This is the composites industry, and there's some pictures from various members meeting activities over the years. We're happy to say that we will be back in person in October in Dearborn, Michigan for our next members meeting, and we're looking forward to that. That's October 5th through the 7th. So we'll look forward to seeing folks there. So today, our three presenters are lined up, and we're going to go ahead and get started with Michael Campbell, who's a technical sales representative at Technical Fiber Products, to be followed by Elias Shakour from BASF and Professor Uday Vaidya from the University of Tennessee, Knoxville. So Michael, I will stop sharing and then you can take over.
Thank you, Dale and Ken, for putting this together. All right. Didn't ask me which screen.
You just need to put it in slideshow mode.
If I kind of sign your name for you just by typing it in.
And again, there you go.
All right. Yeah, hi, everyone. My name is Mike Campbell, and I am the technical sales rep at TFP, and I appreciate you coming to listen today. If there's anything I want this group to take away from this presentation, it's these three things. Technical Fiber Products supplies rolled goods, not finished parts. Our focus is on custom-made, lightweight nonwovens. And we recognize that a successful composite product requires collaboration. We want to collaborate with you. So a brief background on the company. Our parent company, James Cropper, founded Technical Fiber Products in 1986. They make a high-quality specialty paper. TFP's nonwoven manufacturing lines are located on the same campus just north of Manchester in the UK. Our engineering, quality, and rest of world sales teams are there as well. In the US, we have a sales team that covers North America and a metal coating operation there as well. Overall, there are about 120 employees with Technical Fiber Products. So as I mentioned on the previous slide, TFP was derived from a specialty papermaking company. Our nonwovens are made using a modified papermaking process. So here's a picture of pulp, a product derived from wood mixed with water. This is what gets fed into the paper machine. In TFP's process, we have substituted the pulp for engineered fibers like carbon, glass, aramid, polyester, etc. We also use an organic binder to hold the fibers together. So that fiber, water, and binder mixture gets forced out of the head box right here and onto what's called the wire. The rest of the process is just there to remove water. The last step is to reel it up. The reason I'm sharing this slide is so that you have a visual on the inputs and outputs of our process. So our nonwovens consist of short chopped engineered fibers with a specific gravity of more than 1. The fibers are uniformly dispersed, which is something that we take a lot of pride in, and they are held together with a polymeric binder. So in this picture, you can see how porous the structure is. It also shows the chopped fibers with the organic binder. So our main machine lines do not run a single product continuously. Every run is made to order. Bales are not a replacement for structural components. Due to the nature of the short fiber, the continuous fibers in the composite carry the load. In a typical composite project, our bales are in addition to your current layup to add functionality. Our nonwovens are used in a variety of applications. Occasionally, or maybe even rarely, they are used on their own. So like a project like the Whitestone Bridge in New York, our intumescent nonwoven was adhered to the composite wind fairings with a self-adhesive backing. Other times, our materials are coated with our customers' proprietary products. They range from adhesive resin systems to coatings used in hydrogen fuel cells. Today, I will focus on our nonwovens used in fiber reinforced plastics. So as I mentioned on a previous slide, our nonwovens are versatile. Ideally, our nonwovens are placed into your existing layup. Historically, the nonwovens have integrated well into both thermosets and thermoplastics. When utilizing a thermoplastic, we'll need to be conscious of the curing temperature. Here's a list of where our products have been successfully utilized. And on the right is a picture that I took back in Cincinnati, where our IACMI partner was using our veil here in the background during their tailored fiber placement process. All right, moving on to various functions that our nonwovens bring to the part. This is a condensed list of applications by fiber type, and I'll highlight just a few. So glass veils on the surface of a composite part provide a place for resin to evenly spread across the peaks and valleys of a woven product. Our customers use this when they see pitting or air bubbles. Aramid is used on the surface of composite parts, not only to help with surface finish, but to also act as a protection layer. Aramid is very tough and protects from oversanding during production and from abrasion while the part is in use. Examples include the underside of an automobile, cargo containers, or pallets. On the next few slides, I will focus on intumescent and metal-coated veils. So Technofire is an intumescent veil and is made by integrating graphite particles with high-temperature fibers. These graphite particles expand in a high heat situation, and the process is irreversible. In the top right picture, you'll see an illustration of that. So at 190 C, Technofire starts to activate, and by about 400 C, it is fully expanded. All right, I'm going to start a video. Let's see if this works. So in this video, you will see a developmental product that has conductive fibers in the Technofire. It shows how the Technofire expands with heat. In this case, the heat is generated from electric current running through our metal-coated carbon fibers. So you can see the graphite particles starting to expand here, the Technofire expanding. So this would be a before and after picture of Technofire. This char layer, as we like to call it, protects the underlying structure from fire and heat, provides some insulation. And Technofire, like all of our nonwovens, are primarily built into a composite layup. So this is a commercial project where Technofire was added on the outside layer of a composite power transmission pole. This test here was designed to replicate a forest fire event while under load. The fire burned at 1150 C for 3 minutes, and the pole with Technofire was able to handle it. So in this picture, you can see where the Technofire was included and was not included. There was a dramatic difference. The structural fibers were damaged here where the Technofire was not included. The second application I wanted to discuss is our metal-coated carbon nonwovens. In Schenectady, New York, we coat fibers with metal. These fibers get sent to our UK manufacturing plant, chopped, and used in our metal-coated bales. The standard metals that we use are nickel and copper, but we can also do silver, gold, tin, and specialty alloys. We pride ourselves on having every single individual filament coated with metal. We do not coat our carbon bales after the fact. The filaments get coated before they get put into the bale. So this is a conductivity spectrum showing various materials. On the left, you've got your pure copper bus bars, and on the right, dielectric plastics. And we like to play in this region here. So over on the left side would be our copper nickel coated carbon bales. And on the right side would be our dielectric fibers such as glass or polyester. And we can mix materials as well to reach any of these values in the middle. So the primary application for metal coated bales would be EMI shielding for us. We are working with numerous organizations to bring a level of EMI shielding to battery enclosures. In the case of legacy battery enclosures that are typically metallic, which inherently shields from EMI, when switching to a composite, this needs to be thought of in the design process unless you're adding foils after the fact. So when working with these organizations, I'm hearing anything from 30 to 60 dB as the goal. So this here is some ASTM D4935 testing. It tests from 30 megahertz down here on the left side of the domain and up to 1.5 gigahertz. So I like to point out our nickel coated carbon bale, which is the red circle here, at 34 grams per square meter. So still pretty light. And that gets you around 50 dB testing at the low end there and up to 55 dB at 1.5 gigahertz. All right, so my last main takeaway that I wanted to give you was that we want to collaborate. So we have a technical team comprised of highly educated and experienced chemists, materials engineers, whose main function is to work directly with our customers. We can help to identify the challenge. We can provide hand sheets in our lab for new materials. We also have a 20-inch pilot line that we can run new materials on as well. So this here is an innovative list of concepts that we would like to collaborate on with IACMI members. So you've got resistively heated conductive bales. So by running electric current through the bale, it causes them to heat up. This could be applied to curing thermoplastics in situ, warming up the space of a passenger vehicle, or curing thermostats in a mold. Inductive welding with conductive bales. So by placing the metal coated bale in very specific areas of your composite layout and applying a magnetic field, you could target areas to cure. Conductive intumescent bale hybrids. This would be a good example of how we can combine fibers to make a multifunction material. Like in the video a few slides back, you could do this on a larger scale. An example of this would be fire doors in a hotel. Rather than passively wait for the fire to hit the Technofire and activate it, a fire alarm could activate the Technofire and aid in filling the gap between the door and the jamb. Thermoplastic veils such as PPS, PEI, PEEK could be used in your composite layup and melted in place and used as the resin system. So again, my 3 takeaways for the presentation that I wanted you guys to have were, we're a material supplier. We specialize in lightweight, tailorable, functional nonwovens, and we want to collaborate. So I had to throw in a picture here of our last in-person IACMI members meeting. This is me in the at the museum. All right, thanks for your time, everybody, and thanks, Dale, for having us out here.
Thanks, Mike. Good presentation. Yeah, that's I think that's you at the exit of the original Air Force One.
It is,
at
yep.
the Air Force Museum in Dayton. So, yep, it's great, great exhibit. So a couple of minutes for questions if anybody wants to put anything into the chat, but I have a couple that I've generated. On the EMI shielding, where do you place that level, the veil? Is it in the middle of the laminate, top or bottom of the laminate? Where's the best place to put it?
So I think that'll come down to how you design your part, but at a coupon level, it should not matter. So and we're actually doing a lot of testing here for some webinars and conferences in the future. And unfortunately, I didn't have all the data ready, but we're proving that the veil in a composite, out of a composite, and in different layers of the composite, it is actually irrelevant from a coupon level. But when you're designing a part, you may need to think more about how you connect the veil to your gaskets or other parts there to make sure you have a fully enclosed Faraday cage.
A number of years ago, I remember one of the big issues of trying to put composites into, say, large passenger ferries or car ferries was what would happen if a car caught on fire on the ferry itself. And at the time, I don't think a product like this existed, the intumescent. Have you guys looked at that, for composite panels in a ferry, in a marine application?
The short answer is yes. Scott Klopfer, who I'm sure you know, he has a couple projects going where Technofire is being integrated in a marine application. And I don't think I can say anything other than that. Okay. But yeah, we have, and it's going well.
Okay. Yeah, we've got a couple of questions. Yeah, for inductive heating, how much power can be applied before degradation or short circuits happen? And how much depth can be heated with such a veil?
Ooh, I think we'd have to take that offline and work on some trials together.
Okay. And then the last question here is have you done anything to enhance UV protection? Can you make a veil that offers UV protection to the laminate beneath it?
So our veils are inherently porous, and I'm assuming that when you're asking about UV protection, you're a little more worried about the resin system. So theoretically, the sun or your UV rays would be able to penetrate our veils and get through them and into the resin system below. So I don't know if that's an application that would fit our product.
Okay, great. All right. Thanks, Mike. Right on time. And great presentation. And it's neat to see some of these new products out there. Most people historically have associated TFP with just glass and plain glass and carbon veils, but lots of really cool applications that maybe we haven't thought about.
Yeah, that was what I was hoping for. Yeah, thanks, Dale.
All right, good. Thanks, Mike. All right, we're going to move on to our next presenter, who is Elias Shakour. Elias is the technology leader for Composites Technologies at BASF Corporation in Wyandotte, Michigan. So, Elias, please start sharing.
Hey, thank you, Dave. Can you see my screen?
Yeah, just put it in the slideshow mode. And
yeah, just give me a second. How does it look? Good? You see it?
Yes, looks good. All yours.
So Good afternoon, everybody. My name is Elias Shakour, as Dale mentioned, and I work for BASF here in Wyandotte, Michigan. My background is in composites, so I represent a team that works in lightweight composite, mainly for structural and non-structural applications. And my focus, it's myself, is in the polyurethane application, but I have a colleague who works in the thermoplastic application, so we cover the both sides. Today, I'm going to talk about an application that is well known in the honeycomb load floor. We call it spray transfer molding, STM, but we're extending this application to be into the monolithic side of it, which means like I'm taking it and to make more of composite parts where we see there's a big advantage for the high throughput and stuff like that that can enhance the integration of those parts in the automotive industry much easier than other processes. And I'm going to focus more and more in depth in underbody shields for the automotive application where we have a partner that we're working on together. Now, as a transfer molding, you know, when we started, we were focusing on automotive and mainly load floors. But when we have started to investigate more, we built a lab here in Wyandotte as a prototype lab that I will be introducing to you. There we looked into what else can we do and what kind of industry we can serve. And we believe like with this technology, we can serve several industries such as transportation, consumer, construction, and industrial, but we can take it from where you see the upper pictures from the honeycomb load floor, which is really nice, like high stiffness, high strength, to more of a monolithic composite part that with structural application to it. Now, why you would ask why transfer molding is an important fact here. And I took this graph from a paper that I found it's very interesting, like how they present each technology with its strength. And if you notice, pultrusion is way high there because it has high volume of glass fiber, so it's high strength. And then comes the RTM, and below it you can see the spray up, which is spray transfer. Molding could be a part there. But for us, when we wanted to work on it, this is a small area. And if I start looking into increasing more of the glass fiber into it, I can get into the expand the technology and the application by adding more strength to it and fiber content, so I can serve more of a wide variety of application we need by having this spray transfer molding. And it is important to mention with this technology, and I will show you in a minute, it has an advantage of low cycle time. And that's the big advantage. I can have a low throughput part to part within 60 to 90 seconds. And that's where we think this technology can really fit and can be a good fit for a comparable to high pressure RTM as well. Now, how does this technology work? Let me walk you through this video. This is a lab here in Wyandotte, Michigan. This lab is open for our customers to come and bring their tool or use our equipment as well, and our tools to make parts and then go to the OEMs and get their business. So it is open for everybody to come in and utilize the equipment. This technology, let's go back now. This needs started with a corrugated, could be paper, and then we add a glass fiber to it. It could be could be carbon fiber, it could be natural fiber where we are start to use that. We make a plank out of it where you see the core, and then we write a program to localize where we want to spray. And that's the beauty of it. I don't spray places I don't want to spray on. And if you notice, I'm going to pause it for a second. I'm spraying in a 90 degrees. That means I'm not distorting the fiber orientation. In this case, this is a glass fiber, chopped glass fiber. But think about if I have several layups of 090 or quasi-isotropic material, I don't want to distort that, like similar to what happens in high pressure RTM. Here, I am spraying in high atomized pressure on top of the glass fiber, which I really localize the impregnation very well. I just want to say, on top of there, if I want to add more glass fiber reinforced localized, I can add that into the stream of the urethane, and it will be stick to it, and it will be like localized, more localized into the glass fiber. Now I'm kind of creating here a pre-preg. As you see, like we spray on both sides. I want to tell you, in the industry, they spray both sides simultaneously. I want to tell you, once we complete that, this is about 20 seconds on 1 meter square parts. As you can see, then the robot will take it to the mold. And in the mold, I just want to tell you, we can add auxiliaries such as inserts, or I can put a veil or anything else. All will be fully integrated in the tool itself. And this will be in one cycle. We can accomplish having inserts, veil, or in mold coating, and trimmed all at once in one cycle. And the tool is like the cheapest tool, because we don't need to heat it like similar to injection molding. It's, as you can see how simple the tool, this is a heated platen, it closes, and we really get by end of that cycle, demold, you will end having a finished part. So that's the beauty about it. It's fully integrated, that you can add several features in the mold and get you a completed part. So this is like the traditional honeycomb applications. Now to go forward with that, what can we do? I mean, this is well known, as Dale one time told me, but we are extending this application. And so we looked like, we did a roadmap, where can we apply those kind? And this is where the honeycomb application comes in, but I want to show you more of the monolithic. As you can see, we can start from the load floors. This is the tradition. This is what in the industry right now, and there is lots of customers and big volume. You can do the hatchback, that's a monolithic, or you can do it with the paper core. Center console, you can use it, and we are working with customers right now, and this could be natural fiber from jute, bamboo, or flax, and it could be with a core or without a core, and also we can add skin foam to it as well, all integrated in the tool, but the multiple steps though. Sunshades, this could be an option. Now, the next one is the monolithic. That means like we take the core out. So you can do the rooftop. And I want to stop here. With the rooftop, you also can add veils on top, as mentioned, and we can combine it with the rim process, so you can have different colors and be ready as a class A to paint if you want to paint that as well. Fender liner, that's another option. And you can see here, oops, we're going into, oops, what did I do here? Sorry about that. So as you can see here, we're going into the extreme of, like, you would say, oh, that's a very complex shape, but I will show you the parts that we're making, and we can do that. Also door panels and door modular, that's easy to do. And it's lightweight, strength, everything. And we are working with customer on that. Seat pan, this is like, we have done that in Europe and with the BMW. And today I'm going to talk about the underbody panels and skid plates. So this is another opportunities, and we're working with the customer tier 1 on that, but we're serving several OEMs on it. And this is a big opportunity for this technology. So eventually, if you can see it, we're taking that technology and we're stretching it to be more into the monolithic, but we're going to the exterior parts of the car. And that's where we think there's more opportunities. We made this video, but we didn't add also in the battery size, and we have also working on the battery cover and battery top for using this application as well. So So all in all, we think like, where this application can be done. Some of those parts that we are talking about, we are making them for OEMs, and some of them are we are still in the investigation mode, but all those are potential. Now, if I want to go forward, now let's focus more like in the benchmark of the underbody, and this is we work with the partnership with the tier 1 CIE group here in Michigan. They're in Shelby Township, but they have a customer, an OEM customer, and they are interested in they already identify the customer and working on the part with them. So to start with, for the underbody, we went and did a benchmark or roadmap using A2 Mach 1, and we looked at in all kind of underbodies available. And we found out, like, this is an example for the Pacifica. It is quite heavy sometimes. And not only that, if you drive on the highway and you might see some of those underbodies like thrown on the side of the road, because they tend to be with the vibration, they tend to be that joints there, they break fast, and there is some issues. So we thought, like, if we want to go after this market, we have to provide a higher strength. Not only that, it will be a lighter weight. So for this work with our customer CIE, we started with a coupon side, and then we will expand that to a prototype part. So we started with utilizing a polyurethane system that has a biorenewable. It has the highest biorenewable in the market. And we tried to go to the thinnest possible part we can make, which is 1 millimeter. And we did all the mechanical performance for that. So first of all, we were successful to make such a sheet, which is like out of 450 gram per square meter of glass fiber. Not only we did the mechanical performance, we took all the specs that OEM provides, and we did the chemical resistance for it. Those are like the GM and the Ford and some of the foreign automotive specs that we all passed based on that. That means when we passed, that means all the specs passed the requirement. We did also, like, throwing like gravelometers testing and also NVH testing. All of this is under the compliance of the specs that we received from the OEMs. And we went beyond. So what I showed you is semi-structure. We went beyond and we did an investigation for high impact. And that's where we use continuous fiber. So this application can work on continuous fiber. As you can see here, this is a high impact of 130 joule impactor with 4 layers of 0-90 continuous and woven. And you can see the difference of the fracture, but yet it has almost the same energy absorption. We did different DOE studies, and we looked into what kind of a glass fiber it needed for different impact by making specific energy to increase the specific energy, increase the impact energy absorption, but yet to compare it to the carbon steel that it is as the control. And you can see from this graph, like, 5 layers, 4 layers of 0-90 can really be a good fit to replace steel as well. Now, with all the specs that we have done and we pass of them, now it's time to really work on the prototype. And this is the lab here in Wyandotte, and it's open for our customers. For you to come, please reach out if you are interested, you have a project in mind. We have also good skills of simulation of CAE with our groups that we can identify how to optimize the design. This is a tool that we built. It is large, it's the maximum tool we can have in our press. It's about 1.7 meter in length and 1.5 in width. And you can see it has lots of geometry, and we did that has a corrugation. So it could also represent a truck bed as well, but also it has some features that you will see like trim edge and so on. Now, this is this is the part on the left. This is where it is dry fabric, and it could be glass fiber, as I told you, or it could be also a natural fiber, which we did with the flax and jute. We impregnate that. This whole thing took like 90 seconds to really impregnate that. And once we completed, this is a complete part. And as you can see, it's so beautiful, of course, because we really modified the spray to really impregnate on those edges. And you can see how it is well trimmed on the trim edges. This is all in one cycle. And that's the beauty about that. You can get the high strength, add feature into it, and yet to get one cycle. With that, this is a big part. And you can see it has a geometry, complex geometry into it, lots of geometry features in one cycle. As a conclusion, STM, spray transfer molding, is a good technology to manufacture structural and semi-structural composite parts. So eventually we introduced now this technology to be fit where high pressure RTM is long cycle time. We reduced the cycle time to 60 to 90 seconds. So we're offering that as an alternative. We can make large parts, as I told you. Thickness varies. We were up to 5 millimeter without any problems. I just want to tell you this is a good technology for 3D geometry. From the lower picture here, you can see I incorporated a carpet, so you can add carpet to it, and that's for NVH. Or also you can use like a jute flax, or you can incorporate even like basalt if you're interested in basalt. And who is interested in that, and who are we working with right now with the OEMs? Stellantis is one of them, Toyota, Hyundai, and Ford. Those are the target OEMs that we're working with them through our tier, of course. With that, I would like to say thank you, and I'm open for your questions. And if you have any interest in visiting the lab, please contact me, and we can arrange for you to come and visit the lab if you're down here in Wyandotte in Michigan. With that, I would say thank you.
Thanks, Elias. Yeah, really interesting there. This technology's come a long way from where it used to be, simply for load floors and, and honeycomb panels.
Yes.
So, yeah. Well, one question I have, you didn't address this. You obviously talked about glass mats, and you talked about natural fiber mats. But what about recycled carbon fiber mats? Have you done any work in that?
We did a lot with our tiers, and yes, funny enough, like we started with the traditional polyurethane, but because of the nature of the recycled carbon fiber, we developed a new polyurethane that impregnates that very well. So we did that. We work with that a lot, and we have some data with them. Okay, very good. What about thermal performance? What temperatures can you go to? I mean, are these do you have formulations that are e-coat capable or not? Or is that beyond the scope? No, actually the system itself goes to 170 degrees TG. So it is e-coat because, we're working with we're targeting exterior parts, and 170 TG is enough like to hold a e-coat oven of 200 degrees for 20 minutes. So it passes that. The tool itself is heated to 200 degrees, 230 degrees Fahrenheit, and and the cycle that, and we can adjust that based on if you have different veils. Okay. All right. So we need to move on. If other people have any questions, put them into the chat, and I'm sure you can get to those if they pop up. So thanks for your presentation. Very informative. And we'll move on to our final speaker. Okay, so you can stop sharing, and then I'm going to bring up Professor Uday Vaidya. There he is. Hey, Uday. So Uday is the Chief Technology Officer for IACMI. He's also the Director of the Fibers and Composites Manufacturing Facility at the University of Tennessee, Knoxville. And I asked him to present to us
on some architecture-based composites that I think you'll find very interesting here. So, so focus on some beams that won some awards, but he's going to go beyond that as well. So, Uday, it's all yours.
Yeah, thank you, Dale. Thank you all for your time today. So I'm just going to, I think I made a version of this presentation at one of the IACMI members meeting. So this particular application, or there's several applications that fall into the area of large structures, composite structures, fairly unconventional in nature. And this particular one deals with a recreational park application called the Friendship Bell Pavilion in Oak Ridge, Alvin Bissell Park at Oak Ridge, Tennessee. So the history of this is pretty interesting. So after the World War II and the Pearl Harbor and all the events following there, there's been a lot of goodwill between Japan and the US. And so Oak Ridge is a sister city to a city in Japan. And in symbolic to that friendship, actually this bell was made in Japan and then shipped to Oak Ridge. This is basically a 8,000-pound bell, about 7 feet tall, and it symbolizes the peace between the two countries. And so far, this bell was placed at the park, kind of out in the back. And there was an interest from the city of Oak Ridge to bring it out to the front and then feature along with the old, in terms of this technology, some of the latest and greatest technologies that represent the current generation. So they were interested in carbon fiber, also being a lot of history at Oak Ridge around carbon fiber. So these are the architectural renderings of how the structure would look like. And I think in some meetings up at the top level, they decided this has to be carbon fiber beams. And then we were pretty much told, hey, you are producing carbon fiber beams. So that's the history of this whole thing. So the unique thing from an engineering standpoint is each of these beams is 33 feet long, and they're like 36 inches in the height and only about 3 inches in cross section. So they're very sleek and slender, but they're very, very long, like 10 meters long roughly. And there are 17 of these beams that make up the entire structure. And this, I'll show you some images. These beams actually mount onto a superstructure. The unique thing about this is the arc radius of each of these beam is different. And I'll explain that here. So if you look at, there are 17 beams, and this is an example of like B1, B2, B3 up to B17. But this radius at the bottom here is different for each of these beams. So the idea is when they come together, they look more like an arch from looking up towards them. I mean, architects have funny ways of looking at things, but then they kind of came up with this idea that this will be the visual, how it will look like. But being that they are different radii, no single one mold would obviously be able to produce these. So we looked at a lot of the paper exercises on what may work. For example, we considered pultrusion, but the beam had varying radius, arc radius. So pultrusion was not an option. Hand layup would be possible, but it was not very practical. RTM would be a possibility, but each beam would require a unique mold. Filament winding would have been too expensive. Vartim by itself would be a laminate, solid laminate would be too heavy. So we considered or realized that it has to be a sandwich design. And in this case, we therefore gravitated towards braiding. So in these things, the customer has very little idea around composites. So in terms of customer education and getting their buy-in and who will stamp the drawings, and there's a lot of issues that come about. So we had to produce a lot of coupons and touchy-feely things that kind of help the customers realize what these things look like, what the view means, and how can you shape it, and so on. So this kind of exercise took some time to get their buy-in into here's a possible way we would produce this. So the concept here simply is that it would be a sandwich structure. It would have basically a foam core that would capture each radius of each beam. And then the idea is we would overbraid these with the unique overbraiding technology. So therefore producing a continuous but very stiff and highly durable structure. And the fact that these are double cantilever, so they're free floating beams. So which means that the core where they are supported, they would have to have higher density of foam. And then as they go gradually outwards, like an aircraft wing, they would have lower density as you go from the center out. So in concept, that was how we had conceived the design would work. So these are images. I'm going just quickly because of time, but if you look at the center beams, these or the center sections, these are 20 PCF foam in which we actually pocketed out the slight pockets to hold a steel plate that would have the holes through which the connections would pass through. So this kind of the two halves, they mate together and this becomes the center section. This on the right side is the 8 PCF version that basically marries to the center section. And this is the long section out here, so it's much lighter density foam. These are about roughly 3 inches in thickness. The braiding itself, overbraiding, unique technology here. So in terms of course, braiding is common, but in terms of braiding such a large structure in a continuous way was where some of the challenges were. So we collaborated with Highland Composites at the time and basically looked at ways of continuous overbraiding. So these are some images of that as the foams is passing through the braiding section. I'll try to play this video. So the foam continues to advance and then the triaxial braid kind of continues to be weaving around this structure. And so you get the idea of how these preforms are produced. And we had to do several adaptations to the braider here itself in order to guide the foam, order to basically center it, and a lot of small details here, but they do actually provide a very unique way of braiding these. So these are examples of the finished preforms. So we produced about close to 20, 25 to where we made a lot of mistakes in a few, but then these preforms then were staged, would then go through the vacuum infusion process. So in a single step process, we were able to infuse this in about 20 minutes time per beam. So very fast infusion, but the layup does take much longer than that, of course. But we were able to get full consolidation wet out through the infusion. This is an epoxy resin used over the braided architectures here. So the composite beams, actually you can see about 15 PCF at the end, weigh about 200 pounds. Try doing that in concrete, like lifting these two, obviously a huge difference. And then if this were made out of wood, it would be about 500 pounds, about more than 2.5 times that of the composite beam. So all the beams were staged, produced, all the flatness was checked because the top of these were flat. And these are essentially all unfinished at this stage. They had a taper on these sides. So you can see the mark of the taper out here. And then finally the beams were finished and then brought onto the site. And then they were placed upside down first to check for alignment because this rod would connect all of them and pass through it. And this is the same on the other side. So this check had to be done on the ground. And then this was the fixture which would hold them to the superstructure. So you can see this width here. This is where each of the beam would pass, and then those holes that I showed you in the beginning is where these rods would pass through. That's how the beam gets supported to the superstructure. So this is the superstructure here. It's essentially like a L-shaped structure. So this is each of the location of the beams would be out in this position out here with the fixture that I just showed. So for example, as the beams start getting mounted, you can see they're located each in a very unique position based on their arc radius out here. And then the bell is positioned right in the center. And this particular L-shaped structure holds 8,000 pounds of these of the bell, and then very light beams that hang over it at the end of the day. So this is kind of how the complete assembly would look like at the end. And this was done in September 2018. Can't believe it's that long. And this is the finishing of the base of the structure. You can see they're fully free floating, only connected in the center. And each of the beams, after they're installed, the base was left like half complete with half circles, essentially to symbolize the unfinished circle of life. And this was the architect's version of how they would demonstrate this to the community at the end of the day. So this, I must point out, was fully done through student support with about 20 students spending 2 months back and forth with Highland. David Branscombe, I do want to acknowledge him greatly. And this was a little unique application for us, but because of huge involvement and IACMI providing the student enabling support was very significant. This won the Sister Cities Award at Houston, won the CAMEX Award for Most Creative Design. We have published this work as well lately in Composite Structures Journal. And this kind of is the opening ceremony. I'll play this. Show this. So that's the architect Damian Wilbur from Washington. And this is the ringing of the bell ceremony actually. So, and then that was the proud moment for us. So that's a brief on the bell itself. I thought it might be of interest to see. And really John Hopkins and Robin Page, Jared Blue, they enabled a lot of the support that goes into getting these kind of things approved, but DOE's help was greatly appreciated. So recently our team, like Alex Stiles, a student in our team, has partnered with architecture to build like Freeform Architecture, 30 feet tall towers made through additive manufacturing with combination of glass and carbon fibers here. And this particular design is fully modular. The base was 3D printed on the BAM system, but the rest of the structure assembles like a jigsaw puzzle. And it was shown in the exhibit in Columbus. It also has been shown at CAMEX, won the 2020 ACE Award for the most creative design at CAMEX. A lot of industry partnerships here through such projects. So that's a very quick snap through. The last thing is the large scale structures going on in collaboration with Oak Ridge on the building side of things. So there's a lot of effort in terms of a BAM printed tooling for concrete casting, and then looking at rapid construction technologies. So this is a activity in San Francisco, and essentially you can see all these modular elements were printed or made through printed tooling. Like you can see the tool is printed here, machined, the mold is created, then the casting is set up, the concrete is cast, and then precast parts are produced. And these have been demonstrated to go into building construction. So I think IACMI collaboration and some of the partnership is enabling some unconventional uses of composites in large scale structures. So thank you for your time, and Dale, I'll stop there.
Thanks, Uday. I thought you were going to maybe get to that slide on the Raiders torch, but
No, actually, I somehow missed that one, but you can talk about it if you don't mind.
well, I don't have it in front of me, but yeah, there was one of the world's largest 3D printed structures now is the torch at the Raiders Stadium. It was printed on thermwood machines out in Kansas City and then assembled in the stadium. And it's the Al Davis torch. It uses laser light instead of a real flame, but it's let's say it's 86 feet tall. It's a pretty nifty architectural achievement. So for those, I'm sure people who watch NFL football would have seen it, but if you haven't, when you look at the Las Vegas home games, take a look for that thing. But that's 100% 3D printed. So one question here. For the braiding, does the fiber tension allow it to conform to the changing shape, or is it more complex physics than that? So is it the tension on the fiber tension form it around those changing?
Yeah,
let's
no,
call
that's
it
a great question.
perimeter.
Yeah, sure. So, you know, very much so the tension control on the fiber is very critical. And as you can imagine, as the radius gets more sharper, the angle of the braid also continues to adopt. So you may start off with a minus 60, but then at local locations, you may end up with 70, 75, 80 even, right? Based on and therefore the tension plays a huge role. A little bit of weakening of that is going to start causing wrinkling and another effect. So changing fiber angle locally is also a great function of the tension. And that's why all those fixtures I try to show adapted to that kind of, you know, the foam tended to do this over that length, keeping it straight and same time continuously progressing at an even rate. So all of those were process development factors.
Okay, great. Okay. Well, we're pretty much at the end of the hour, so I appreciate your contribution to this, and as well as to Elias and Mike for their contributions. We don't want to extend past 1 o'clock, so I want to thank all of you for attending today. If you have any questions for any of the panelists, feel free to send them to me. You can find my address on the IACMI website, and we'll be happy to get those answered for you. If you need to reach out to them, we can provide that contact information as well. So thank all of you for attending, and we will see you next month on July 19th.